Okay, so tonight we'll talk about our next topic, which is calculating machine cycles and also about loops. Now, we understand plenty of branches. So the branches are the main instructions for the looping, because as you have seen that we can branch backward. That's how we can control the loop. Like if you keep branching backward and running the same lines again and again, that's how the loops work. Okay. But one important thing here is, before we start with the loops, we also want to talk a little bit about the runtime. In the low-level language, since we deal with since we deal with so many instructions in low level.
You don't use that tonight?
Yes, I'll take care of that.
I have a board over there still out.
Oh, okay, so let me lock it then I'll open it again. So we have a way to use, just when you use the low-level language, like the ones we have here, you can calculate the runtime of the instructions. Like, let's say you know the speed of the processor, and then using that information and some other information, you should be able to calculate how much time you need to run a certain block of lines of code. Now, this is pretty unique in low level, because you probably cannot measure it at the high level because things are so abstract. It's really hard to measure that. That's also another, I think, special feature of the low level. So tonight we'll see that how you can pretty much use the instructions. These are the basic, some basic things that probably I think we have, we know, but we probably don't have too much clear idea. So for an example, like all the microprocessor, no matter it's a cell phone or desktop or any microprocessor, laptop, the microprocessor generates some clock cycles. And all the clock cycles are just like these are square waves, like pulses, right? And when one cycle means it starts here, right? And it goes all the way to here to complete one cycle. Now, for an example, if you have a 2 gigahertz microprocessor, it basically generates 2 times 10 to the power 9 cycles per second, right? Now, think about the cycles. So it's 2 followed by 9 zeros. That many cycles in 1 second. Now, the instructions require these cycles to be executed. For an example, let's say I gave you an example here. Let's say this is an instruction, LDA pound $25, which is an immediate instruction, immediate move instruction, right? So this requires only 2 cycles to be executed. Now think about the microprocessor, that how many instructions like this one it can execute in 1 second. It's generating 2 times 10 to the power 9 cycles per second. And this instruction only takes 2 cycles. So it's pretty much generating 1 followed by 9 zeros number of instructions like this one, which is huge amount of instructions it can. That's exactly where the microprocessor basically beats the human beings, because we can do the same calculations and same math and same thing that the computer is doing, but you cannot beat the runtime. So, to understand the machine cycles, meaning how many cycles you have in, or maybe let's say I would say to understand the runtime, we need to calculate the machine cycles, meaning cycles required to run a block of or bunch of lines of code. What do you need to know? You need to know addressing mode. I think we now pretty much understand addressing mode. We have a clear understanding of all types of addressing mode we have. We also need to know the machine cycles required for each instruction. So the machine cycles are found with each instructions, with each mode. the required cycle you have on the column 7 of the set of instruction. If you just open the set of instruction now, if you check this column 6, you will see there are plenty of numbers written in decimal. Those are the cycles you need for different instructions for different mode. Because for a same instruction, if it is in different mode, it requires different number of cycles. Cycles mean one pulse, complete cycle of a pulse. We need to know one additional thing, which is called pseudo op. We don't know what it is yet, but we have been using pseudo op for a while, but we don't know what it is. Now, the pseudo ops are some sort of assembly commands. These are not your set of instruction. I'm saying the instructions we have, but these are some sort of commands we write in the low-level language. Like, remember, for an example, org. You have written org in every single program, right? Org or like FCC, FCB, those kind of thing, or EQU. You have written those things in pretty much everywhere, but those are not exactly the machine. I'm saying the instructions we have been writing, because as you can see the set of instructions. We don't have any of those there, because those are not exactly the set of instructions, but those are something called assembly commands we use to interpret something to the assembly. So we'll tonight see those things too, because those will be required to understand to calculate the machine cycles in some cases. And also for those we don't have any like object code generated, but those have different purpose. We'll see also. For an example, I took a couple of pseudo op, like the ones which are most important. We use it pretty frequently. One of the major, I think important one is the org. Every single program will need it for sure. No matter what program you are writing in 68HC11 series for 68HC11 series Motorola microprocessor, you have to have one line with org for sure. No matter what you are writing, you must have to have it. Okay? Because that basically specifies the location for the assembler to deposit your machine code, meaning where to start the code. Because you have a bunch of locations starting from 0000 to all the way to FFFF. Now your microassembler has to know where it will start depositing your object code once you compile it. And we pretty much most of the cases mentioned is D000. You might be wondering why it is D00. That has a different reason why it is not 0000. We don't save it from the starting location, right? We save it starting from D000. That's a different purpose. But you can change that location anytime. I'm saying if you know exactly how the memory is organized, meaning how the data are organized in different places of things, then you probably should be able to know it. But and I tried to give you an example. But remember, every single program will have to have this line. One time, maybe multiple times, but you have to pretty much specify where you are trying to store all the code, object code, once you have the object code. Remember, the object code and machine code, those are the same thing in this class. Sometimes we use object code, sometimes we use machine code, but we know exactly how the object code look like, right? So pretty much those are the machine code. But remember, in the machine, everything is stored in binary. We write it here in hex, but that's the same thing. This is another one. I think you have seen this one as well, EQU, right? I think this is something we use to equate a symbolic label to a numeric value. You might be wondering why it is. We need this one. For an example, let's say you have plenty of ports in the Motorola microprocessor, or let's say the Fox trainer board. We have never used the board yet, but I'm saying any of the port yet, but we'll be using those soon. I know that some of you probably cannot wait, but I strongly recommend to wait, but we'll be there for sure. Now remember, all the ports has an address. Each of the port has an address, and that is an unique address defined by the Motorola. It's given, it's predefined. But we have a list of those addresses. But the thing is, whenever you will be using those ports, you don't want to memorize all those addresses. Instead, what you can do is you can just write some line like this. Port B EQU 1004. I'm saying 1004 $. That means this is the address of the port. So after this point onward, you will be able to write just like this, LDAA port B. Now your microprocessor assembler will read it like this. Because every time you write LDAA, LD, I'm saying port B, it just replaces the port B by 1004. So the good thing is you don't have to memorize the address, because it's easy to memorize the names instead of address, because all you need to remember is, okay, this is the name of the variable, but I don't want to remember the address, because there are plenty of addresses around and you don't have to memorize all the addresses. That's doesn't make sense. So remember the reason we are talking this is important, because let's say I just give you this line, LDAA port B. Just by looking at LDAA port B, you will never be able to identify what is the addressing mode, right? Unless you know that these lines means LDAA $1004. Because when you know these, that LDAA $1004, you know that addressing mode is extended, right? Is anyone here who has a doubt that this is not extended? The addressing mode of LDAA $1004 is extended, right? Okay, so that's why we need to understand what the EQU means, because every time you write with something with EQU, so you are trying to equate the level port B with 1004. So pretty much every time you write port B, it get replaced by 1004. For an example. So another example is this. I think you have seen it as well. Many times we used, I think, some sort of text, and we tried to print the text. Now when you do that, you always try to use something like this, FCC. So the meaning, the meaning is form, not the meaning, but the abbreviation of this one is form constant character, which basically deposits a text string into object code. What it does is it basically stores the string as an object code. Now you might be wondering how it is possible. Remember, the string is nothing but the sequence of characters, and each character has an ASCII. So all it is storing is the ASCII of those characters. And each character has a unique ASCII, right? I'm saying each letter has a unique ASCII code. So and again, this is about the data. Whenever you do not store the ASCII, but you probably are storing like bytes, you can do these. And what the good, so DB1 C008. So FDB means form double byte. I'm saying whenever you write these, you can store a double byte. You see there are 2 bytes, right? C008. But when you want to store just 1 byte, so these are some sort of, you can compare these just like the variable declaration in the low-level, high-level language. What do you do in the variable, high-level language? You write a variable name. You just write, let's say int, the variable name is a, and then equal 25. What does it mean? That means you are defining a variable a, and you are also setting the value of a is 25. So it's pretty much the same thing. What you are doing here is, you are saying, okay, I have a variable SB1, and the value of the variable is A5. It's pretty much the same idea. Same is this one, but things are a little bit different here. It's not like the high level, because in the high level we have integer, we have float, double, character, plenty of different types of, even in object-oriented programming, you can create your own class of variables, right? I'm saying you can create the object from the class. So I'm not going towards that direction. I think you probably have little idea, but you have plenty of, I think you should have some ideas about the variable names, right? You know how to define the variables, right? So, but here we have the variables all in terms of bytes, or like, because we are a little bit in the raw mode. Okay. So, and also sometime what you can do is you can use RMB. I think you have seen RMB as well, I think somewhere in lab 2. RMB means reserved memory block. What you can do is RMB is you basically store, you basically can reserve some bytes in sequence. For an example, if I write this line RB1, RMB20, for an example, RB1 is again name of the variable. What you are doing is, using the name of the variable, you are reserving 20 consecutive bytes. It's 20 because I wrote 20 here. I could have write 15, I could have write whatever I need. So what it means is, whenever you are storing the object code from the beginning, let's say starting from D000, all the object codes are stored in sequence. But whenever you are writing these lines, at some point, 20 blocks, I'm saying 20 bytes will be just blank. And then again something will be stored. So it's something like you are putting a gap. But there is there are probably some reasons behind. You probably want to use those, those 20 byte later on, or maybe, this is probably something like when you just define a variable but you do not assign the value in high level language. Just say int a. That means what? You are defining a as an integer, but you did not say what is the value of a. Later on you probably have defined a, or you are using a, or whatever you do want to a, right? So these are different things you can, but remember, all these terms like RMB, FCC, FCB, FDB, or ORG, these are the pseudo ops. Okay, because these are not exactly the Motorola instructions, but these are the assembly commands you always want to use with your assembly compiler to tell compiler some sort of special thing that you have seen here. Now, why we need this, we'll see it soon. But at this point we just have some idea about the pseudo ops. Now let's go back to the machine cycle calculation. Now let's say I want to, again, we are heading towards calculating the runtime. But to understand the runtime, we first need to know how many cycles we need to execute some sequence of lines. Now for an example, we have 3 lines here. I'm sure that we need more lines, we want to see more lines, but we probably want to wait a little bit again. So we have 3 lines here. Okay. Now all you need to know here is what is the addressing mode of different lines. Now if you check your set of instruction now, and if you check the column 7, you will see, for an example, the first line is what? Immediate, right? Line 2 is what? What is the mode? Direct. Third line, extended. So if you go to the set of instruction and check the column 6 for these instructions, for this specific mode, you will see it's mentioned there in the column 6, I'm sorry, column 7, I guess, column 7, that you will get the cycles from the column 7 for each of the mode. So first instruction will take 2 cycles, second one 3 cycles, last one 4 cycles, so total is 9 cycles. So it's pretty straight to find it, right? As long as you know the addressing mode, this is straight. Now, the second thing is little bit modified version, the ones that we use. Now let's say I have this code. Okay, so let's say I'm trying to find the machine cycles for this line, LDAA1. How do I know it? Now the first problem here is I exactly don't know how to calculate the cycle of this line because I don't know exactly what is the mode. Do you see the problem? Now, to know this, you pretty much have to understand the pseudo ops. That's why you talked about the pseudo ops just a while ago. So A1 here, how will you define A1? Look at this. A1 is defined here. I just said A1 FCB 48. Now that means A1 is a label, right? Which is, again, you can compare it as a variable name for an example. But remember, anytime you write this sort of thing, the compiler assumes you are replacing A1 by the address of A1. Anyone tell me what is the address of A1? No, 48 is not the address. 48 is the data. We know the difference between the data and address, right? Now, look at this carefully. The first line tells you where the object code started. So the address is there, which is 0010. So pretty much A1 is the first byte, right? So the address of A1 is 0010. So your compiler will read this line like this. But you might be wondering why I have written 0010 as 10. There is a catch here as well. Whenever you see some address which can be written as 1 byte, because 0010 can be written as 10, right? That's the same thing. You always want to do that because direct addressing saves a little bit than extended, because you probably remember when you write the object code, extended always takes 3 byte, direct always takes 2 byte. Always people, I'm saying efficient people want to save storage, right? Whatever you can write in 2 byte, don't use 3 byte. That's the idea. So it's read by like this. So A1 is replaced by the address of A1, which is 10 in hex. So now you know the mode, which is direct. If you go to the set of instruction and check the direct mode of LDAA column 7, you will see that's 3. You want to make sure that you see 3 there, okay? Column 7. Now let's add a little bit here. So let's say I added one more line here. Now let's look at the difference here. Look at this situation here. I first started storing from 0010, and then I defined a variable. And later on, I again started from a different location, because anytime I can start from different locations just using org. I said, oh, let's start here, let's start here. I can, I can jump around different, locations in the memory map. Now I started in a different location and I stored another variable here. Now, as you know from these two lines, that A1 and B1 in these two lines will be replaced by their addresses, right? As I think we already know about the A1, but how about the B1? See, the B1 address started from where? 1010, right? Now you see might be a little bit difference here, because the first line you were able to write 0010 as 1 byte, but you cannot write 1010 as 1 byte. You must have to write in 2 byte. So that's why there is a little difference here. The first line is direct mode. The second line becomes extended. And cycle has a difference. You see, if you go to the column 7, it's always different because its mode is different. So that's how we can figure it out. And I'm sure that you will enjoy the quizzes because you will see plenty of these. Now let's change a little bit. Look at this. I marked it red, because I just replaced the FCB by EQU, because EQU is a little bit different than this. Now what happens if you have EQU instead of FCB? Because remember, EQU always tells that B1 and 58 are the same thing. But anytime you see B1, replace it by 58, not by the address. So now you see the change. Look at the red marked. Do you see the change here? Because now anytime you see B1, that gets replaced by 58, not by the address of A1. Remember, previously it was address of B1, right? But now this is not address, this is the data of B1. So be careful about the EQU, which is a little bit different than all other ones. Yeah, EQ always replaces, whatever the equivalent, because it's just like equating. Remember I said the level and the data, those are equivalent, so So see, these pseudo ops are pretty important at this point, because if you don't understand pseudo ops, there is no way you will be able to understand the addressing mode, and there is no way you will be able to find out the cycles. Okay, and we always use the pseudo ops, because that's how we write the code, because we want to use the variables, some sort of labels. Okay, now I'm sure we will see and we'll be able to practice some sort of things in the quizzes. But again, let's talk a little bit about the runtime, because remember, the plan was to see the runtime or calculate the runtime. Remember these lines we started with at the beginning, and we know that we have 9 cycles here. Now let's say we modify the question a little bit. We know there are 9 cycles, but we also know that the microprocessor we are using, for an example, is 2 gigahertz. That is defined. That's somebody told us that the microprocessor, the speed is 2 gigahertz. Now how do you know that how much time you need to run these lines? You can know it pretty simple, because there is a very basic formula. Runtime equals to total cycles divided by processing speed. So the runtime was, total cycle is 9, and the runtime is what? 2 times 10 to the 9, right? That's the 2 giga, right? I'm sure that I'm assuming that we know all those things, right? Giga, tera, pico, nano, we know this, right? So let's go back, and then you can calculate it, and 4.5 nanosecond, right? 10 to the negative 9 is nano, right? You see how small the time is. I'm saying it's really hard to identify 4.95 nanosecond. You might see it's instantaneous, but it's not. Okay, but remember, it's not 3 lines. Whenever you have 3,000 lines, that makes a sense. You will see the difference. Sometime you might see, okay, you have written the same thing in 50 line, the same thing in 48 line. You might be wondering sometime the 50 lines is taking less time than 48 lines, because the instructions you are choosing in 50 lines may have less number of cycles than 48 lines. You understand what I'm saying? Because at some point it all matters, because remember, The people, it's not probably too important at this point to us, but it's important to the people who is designing the operating system, designing all sort of different software, like the very basic but bigger software, because you probably have no idea, even the microprocessor people, let's say the Microsoft people who has been working extremely hard to design their new operating system, they have been like struggling just to save like 5-second booting time. Probably they have been spending 1 month just to save your 5 seconds while you are booting. That 5 seconds is quite important. You see how many instructions you need to save 5 seconds. But that 5 seconds is quite important to their user, because you are not happy with the booting time, because it's still after all the modifications and hardware, microprocessor speed, still you are not happy. And they always want to make you happy, but at the same time they have to give you the service. You probably, I have some of my friends, those who were with me in my undergrad, they have been now in Microsoft, so they are pretty straight. They have been working there for the last 10 years. They were there when they designed like Microsoft starting from Windows XP. Now they compile, because at some point, whenever the integration part, they have to compile the whole program code. Even the Windows 98, it's an older one. I'm not sure have you even ever seen Windows 98. The Windows 98, the code was at least like 3 million lines. The Windows 98 was the oldest one. Now I'm not going to query about probably the Windows 7 or 8. That will be probably biggest lines of. But remember, they're adding more lines. They're trying to save you time. Think the challenge. But the good thing is, microprocessor has faster speed these days. I'm saying it can generate more cycles. But there is a trade-off. Whenever the machine gets faster, software gets bigger. But there is always a catch between these. And people who are designing microprocessor, who are designing your main board, I'm saying the motherboard, who are designing your graphics card, they have been struggling every single moment to save time here. And they exactly know how many cycles they want to save, just to save you time. Because at some point people compare, okay, let's see which one is faster, OS or Windows 7. So don't you think that they have been they have been doing all sort of research to save their time, because they know that at some point those will be matter. People will be, discussing those in blogs, in newspapers, in different places to see, oh, this operating system is faster, this is slower, You see all sort of those things, right? For an example, these days people have been talking about the Android. I'm saying now the concentration is really different, because they talk about the Android and iOS. I'm saying the iPhone operating system. But again, we still have the same thing there as well, because there are cycles. They want to save the time. They have processors. They are trying to save time, but at the same time, they want to also keep the processor cool, because if the processor is working too much, processor gets hot. Your phone gets hot. You don't want your phone. You always want your phone to be cool. There are all sort of these things. But again, all the source of all these things is coming from here. This is not the class where we probably running after these things, but we probably will have some sort of idea that where all these cycles and calculations are coming from. Again, we have only 2 quizzes from this part, and once we are done here, the next thing, or probably in the next class, we'll start talking about the loops. We are pretty close to the loops right now, okay? Because we know how the loops work, because we have pretty good understanding of the branches. But with the loops, the most important thing we'll be talking about is calculating the cycles for the loops. That's a little bit different than regular cycles here, because in regular cycles we just we just add the cycles and sum it up. But in case of loops, some of the lines are running multiple times, right? So you have to consider the cycles multiple times. So we'll see those things later, probably soon, but sooner in the next class. But let's finish these 2 quizzes, and in case I have seen that probably most of you are done with the last lab, which was lab 3, and also, except I think 2 people, and also the pre-lab 3C, because we soon will start talking about the lab 4 before even we go for the break. Okay. So, and these are also part of the lab 4, whatever we'll be discussing here. Meaning all these machine cycles and loops. Yeah, we'll start the lab 4 before that point. Okay. Okay, so let's start the presentation. Let's stop the presentation here and then